Alright, this will finish up chapter 7. So working backwards, now that we know how to find the probabilities, now we're going to have to work backwards to find those target values. This is on page 342 of your textbook. So if you are given a probability, which is usually in the form of a percentage, and you want to find what I call the target value, we can again use the chart or the calculator. I think most of you will prefer the calculator. So using the chart, you'll have to determine if we need to subtract that probability from 1. Remember, if it's a greater than probability, or if it's an upper probability, which you'll see, you'll have to subtract from 1. That's also true if you're going to use the calculator. You might have to subtract that probability from 1. Then you can look up the probability in the chart as close as you can, or you can use a function in the calculator called inverse normal. If you use the chart, you look as close as you can, and that will give you your z-score. Then you use the z-score formula to find the x value. So these two steps require, or step 4 requires a little bit of algebra. If you use the function inverse normal, you enter the area, which is the probability, to the left, the mean, and the standard deviation. That will just spit out the x value. Otherwise, you can just enter the area, or the probability, and it will give you the z-score. So sometimes the MyMathLab will want the z-score, sometimes it will want the x value. And that's if you don't need the x value, you can just enter the area, and it will give you the z-score. So we'll kind of look at both ways and see how they work. So using that same situation with the heights of female 3-year-olds, we're going to find the height of a 3-year-old female at the 20th percentile. The 20th percentile. So that covers 20% of the curve. So let's just draw a quick sketch to remind us what a percentile is. Someone at the 20th percentile means that they are taller than 20% of the rest of the females. So the target value x means that 20% of the girls are shorter than that value x. Remember that the mean is that same 38.72, and the standard deviation is still 3.17. So the 20th percentile represents the bottom 20% of the curve. So we do not need to subtract from 1. We're going to use the area 0.20, which represents 20%. We're going to try to find 0.20 in the middle of the chart, which some students are really good at, and some students this drives them crazy. The numbers start in the top left corner at 0 and get bigger and bigger and bigger and bigger and bigger down to almost 1 at the bottom right of the chart. 50% is roughly in the middle, just to give you a reference point. So if you look in this chart and you're looking, we're looking for 0.2000, or as close as we can possibly get, which in this chart is 0.2005. That's as close as we can get. And then we'll look backwards and see that it's negative 0.84. That's as close as we can get. So looking that up, we get negative 0.84 as a z-score. And we know that the z-score formula is x minus mu over sigma. We're trying to find x. We have z, mu, and sigma. So z is negative 0.84 equals x we don't know minus the mean from before, 38.72, over sigma 3.17. And then you'll use your algebra skills to solve that. The textbook formula chart did help you out a little bit. If you look in chapter 7, it does rearrange the formula to solve for x. So that might help you out a little bit. X equals mu plus z sigma. I don't like all that rearranging. I just use the algebra. So algebraically, this would be negative 0.84. We would multiply by 3.17 and add 38.72. So we're undoing the operations to get x equals 36.0572, which is about 36 inches. So a lot of students do not like this. They do not like looking in the chart. They do not like doing the algebra. So there is the calculator method, which most students prefer. In the calculator, again, we need to know that the area we're referring to, area to the left, is 0.20. And so we're going to do inverse normal, which is also under second vars. Should be the third option if I'm not mistaken. Second vars, inverse normal. The newer calculators will prompt you for the area, the mean, and the standard deviation. The older calculators, we have to remember the area, the mean, and the standard deviation. You type in all three of those. 0.2. Let me just show you real quick. If I just put 0.2, it spits out the z-score, negative 0.84. So some homework questions just want the z-score, so you just put in the area, and it spits out the z-score. If you want the target value, you type in all three things, 0.2, 38.72, and 3.17. That spits out 36.052, which again is about 36 inches. So a lot of students prefer the calculator method just because you don't have to look anything up or do any algebra. So if you can remember area, mean, standard deviation, and that will give you what we call the target value x. I think I have one more example here. Yep. Alright, one more example of working backwards. This is example 4 from page 343. It says the scores earned on the mathematics portion of the SAT are approximately normally distributed with a mean of 516 and a standard deviation of 116. What scores separate the middle 90% from the top and bottom and top 5%? Alright, so I'm going to draw a picture. You don't have to draw a picture, but I like to just to kind of visually help myself out. So nice good curve, nice and big so you can see it. We have 516 in the middle. 1, 2, 3, 1, 2, 3. We're going to add 116 3 times. And one more time. And then subtract. I believe that's 400. What'd I do? Subtract again. And one more time. Again, we're just trying to get a span of values to help us make sure that our answer is reasonable. So from here, we want to know what scores separate the middle 90% from the bottom and top 5%. So it'll be somewhere in here-ish. That's the top 5%. And somewhere, let's see, somewhere in here-ish will be the bottom 5%. So we don't exactly know where those values hit. We're trying to find a target value. I'm going to call that x1, and we're trying to find this other target value, x2. It might actually be over here some more, but we're just kind of getting a sense of what we're looking at. We have the middle 90% somewhere in here, and then I think it's somewhere in there, and then the target value for the bottom 5% and the top 5%. So it just kind of gives us a visual and kind of guesstimates where our values should be. So we're looking for 2 x values. So we can use inverse normal. For the bottom 5%, we'll just put in 0.05 because that's to the left, and then the mean and the standard deviation. And we'll do this again. For the top 5%, though, the top 5% is to the right, and remember we need to default to the left. So the opposite of the top 5% is the bottom 95%, the middle and that bottom tail. So we're going to put in 0.95 and then 5/16 and 1/16. And it will give us our two target values. So inverse normal 0.05, whoops, comma 5/16, comma 1/16. That gives us 325.2-ish. And then inverse normal again with 0.95. And that gives us 706.8. So it's about 325 and about 707 if we round all the way off to the nearest integer. And your homework will show you how it wants you to round. So it's using inverse normal. Always defaults to the left, so if you're looking at the top or the upper or the greater than side, you always have to subtract from 1. And in the calculator, put in the lower side, put in the less than side. So that's again using inverse normal to work backwards and find the target value. This textbook has some special notation. It uses a little alpha symbol. That's a lowercase Greek letter alpha. Now alpha in this textbook is used for a lot of different things. In this particular chapter, it's used to represent the area to the right of the z-score. Which is kind of counterintuitive because we've kept going to the left, to the left, to the left, and now this notation goes to the right. So this is called z sub alpha. Sub means subscript, so z sub alpha. It is the z-score such that the area to the standard normal curve to the right, the area under the standard normal curve to the right of z alpha is alpha. So it's a little tricky. They're not trying to be tricky, it's just a weird notation. So if we have this weird notation, I think there's one in your homework. I don't put it on the test because I don't like the notation. But this is z with a little alpha of 0.10. On a curve, it's asking for the top 10%. So it's the top 10%. So we're looking for the z-score, z-score of the top 10%. Now we can't put in 10 because that's the top. We have to put in the opposite or the lower side of this. So what do we put in the calculator? 0.90 for the area. So in this situation, you would just do inverse. Y'all can't see that. You would just do inverse normal of 0.90. We're not working with a mean and a standard deviation. We're just trying to find a z-score. So inverse normal of just 0.90 or 0.9. And that's it. And the answer it gives you 1.28 is the z-score. And that's what we're looking for. So these are just generic problems. They don't have scenarios attached to them. They don't have means and standard deviations. It's just looking for particular z-scores given different levels of what they call alpha. It always defaults to the right, so we always have to take the opposite. Any number it gives you here, you take the opposite of that number, or 1 minus that number, and that's what you look up in the calculator. So there's a couple questions like that on your homework. Hopefully not too bad. The book mentions this one note. Unfortunately, it generally confuses students, and it's really trying to clarify things, but try not to overthink it. Remember in chapter 6, it was very particular how these little symbols looked. It was very important how the inequalities faced, and if they had a line underneath or not, it made a big difference. In this chapter, these lines, whether it has a line or not, does not matter. So it's not as particular as chapter 6. So don't overthink this. I know this looks really confusing. Just remember that it's not as particular as chapter 6. The book is just trying to explain that we don't really need to worry if it's just a less than symbol or if it's a less than or equal to symbol. They're saying that all of this, all of these little particular differences all mean the same thing, unlike in chapter 6 where it's very particular. So don't overthink that. Don't worry about that. It's just a note to clarify, trying to make things easier for you. All right, I think I have just one extra example here that I pulled out of the book, question number 40 from your textbook, just to kind of pull all of this together. You probably don't have enough room on your page, so I'd get sheet of notebook paper to help you with this one. So this is a Wendy's drive-thru. Fast food restaurants spend quite a bit of time studying the amount of time cars spend in the drive-thru. Certainly, the faster the cars get through the drive-thru, the more opportunity for making money. So this magazine studied drive-thru times for fast food restaurants and found that Wendy's had the best time, with a mean time spent at a drive-thru of 138.5. Assuming drive-thru times are normally distributed with a standard deviation of 29 seconds, answer the following questions. So before we look at any of that, just from reading this scenario, we can make a lot of conclusions and we can actually start setting up our problem before we even know what the question is going to ask. So I'm going to cover up all that. Just given the situation, we find those keywords normally distributed. As soon as we see that, we can draw a nice curve. Always draw these nice and big on your scratch paper so that you can see what you're writing. So our mean was 138.5. 3 standard deviations in both directions. 29 seconds is our standard deviation. So we'll add 29. 167.5, add 29 again, and add 29 again. Always take time to write these out. I know it's a little tedious, but it really helps your brain visualize the problem. Our brains really like these diagrams to help us see what we're looking at. So take the time to work these out, and you'll be glad you did. So nice empty bell curve with 3 standard deviations to the right and left of the mean. This is kind of our working template, so we'll answer the questions using this visual. Now we can look at the first question. What is the probability that a randomly selected car will get through the Wendy's drive-thru in less than 100 seconds? So 100 is somewhere in here. Less than would be over here. And so we can use our normal CDF. Remember that this goes all the way to negative infinity, which we use negative 10 to the 99. So if we just look at the shaded region, we're looking for the left and the right, the lower bound and the upper bound. The lower bound here is 10 to the 99, and the upper bound here is our target value of 100. So our normal CDF has a lower bound of negative 10 to the 99, an upper bound of 100, the mean 138.5, and I ran myself out of room, standard deviation of 29. So I like to see that written out again on your scratch paper so I know where you got your numbers from. So normal CDF, negative infinity to 100, mean of 138.5, standard deviation of 29. So normal CDF, negative 10 to the 99, upper bound of 100, mean of 138.5, standard deviation of 29. Oops. And you should get 0.0922. I always like to have 4 decimal places, so I took that 5 and rounded that to a 2. That's about 9% chance that they'll get through in less than 100 seconds. I'm going to change colors so you can see a little bit better. Question B, what is the probability that a randomly selected car will spend more than 160 seconds in a Wendy's drive-thru? So 160 is somewhere up here. More than would be this side. Remember, this continues to infinity, or positive 10 to the 99. So more than that. So again, For lower bound, upper bound, you just look at the shaded region. Left is lower bound, right is upper bound. It's that simple. Some students like to label lower bound, upper bound. So for part B, we're also going to do normal CDF. Lower bound this time is 160. Upper bound is 10 to the 99. Mean is 138.5. Standard deviation is 29. So second bar is normal CDF, 160, 10 to the 99, 138.5, and 29. And our answer for part B would be 0.2292, which is about 23% chance that they'll spend more than 160 seconds in the drive-thru. Change colors again. Part C, what proportion of cars spend between 2 and 3 minutes in the Wendy's drive-thru? Now be careful. We've been talking in seconds, and now they're switching to minutes. Hopefully that triggered because the numbers we're working with are big, and then 2 and 3 are super small. So remember, 2 minutes would be 120 seconds, 3 minutes would be 180 seconds. They're not trying to trick you, just pay attention to your units. So on the curve, 120 is somewhere there. 180 is somewhere up there. So we're looking between those two, which is kind of the majority of the middle of that curve. So 120 to 180. So I'm just going to put in CDF to save myself some space. These are nice because it's easy to figure out your lower and your upper. So 120 to 180 with a mean of 138.5 and a standard deviation of 29. So you can write in CDF to help just abbreviate, or you can write normal CDF. And I got 0.6620, about 66%. So that's a pretty big proportion. All right, and finally, change colors again. Would it be unusual for a car to spend more than 3 minutes in the Wendy's drive-thru? So again, 3 is 180. So we're using that same target value, 180, but now we're looking at the more than or the greater than side. So the 180 now becomes a lower bound, and the infinity, is still an upper bound. So we're going to go ahead and calculate this. Normal CDF, lower bound is 180, upper bound is infinity, 138.5 and 29. Depending on what we get will help us answer the question. So the percentage we get will help us answer if it's unusual or not. Got 0.0762. Let me make sure, 180 to infinity. There we go. So we get 0.0762, which is about 7%. Remember, unusual is when it's less than 0.05 or less than 5%. So is this unusual? No. So not unusual, because it's greater than 5%. So if it's greater than 5%, it's not unusual. If it's less than 5%, it is unusual. So this helps us kind of gauge what's normal and what's not so normal. I'm going to pause there, and then I'll finish up with the last section from the textbook.